Put your hand flat against the door of your refrigerator right now and slide a magnet up to it until you feel the snap. That short pull through a millimeter of air is the entry point. You have just performed an experiment that classical physics is mathematically forbidden from explaining, and the rest of what follows is an honest account of what is actually happening inside that piece of metal in your fingers. The magnet weighs a few grams. The force you felt is roughly 1/10 of a newton at typical fridge magnet distances. The number worth holding in your mind is older and stranger. In 1919, a young French physicist named Leeuwen and independently a Dutch student named Hendrika Johanna van Leeuwen, working under Hendrik Lorentz, finished a calculation that had been begun by Niels Bohr in his 1911 doctoral thesis. The calculation was simple in spirit. Assume electrons are tiny classical particles. Assume they obey Newton's laws and Maxwell's equations and nothing else. Now compute the average magnetization of any chunk of matter in thermal equilibrium. The answer that fell out of their pages was exactly zero. Not small, not approximate, zero. This result is now called the Bohr-van Leeuwen theorem, and the number to remember is 0 amperes per meter of magnetization for every material in the universe under purely classical rules. 0 in iron, 0 in nickel, 0 in the strip of neodymium pinning your grocery list to the door. The magnet in your hand is, by the strict accounting of classical mechanics, an object that should not exist. It does exist. So something deeper is running underneath. That deeper thing is the quantum property of electron spin, and you carry it in every atom of your body. Each electron in the magnet has a permanent intrinsic angular momentum of 1/2 of the reduced Planck constant, which works out numerically to about 5.3 times 10 to the minus 35 joule-seconds. This is not the electron rotating. The electron is not a tiny sphere whirling on an axis. If you tried to model it as a spinning ball of the measured electron radius, the surface would have to move faster than light by a factor of several hundred to produce the observed angular momentum, which is the experimental fingerprint that tells you the classical picture is wrong before you even open the math. Spin is intrinsic. It comes with the electron the way charge comes with the electron. It can only be measured along any chosen axis as either plus 1/2 or minus 1/2, never anything between, and that pure two-valuedness is itself a quantum signature with no classical counterpart. Each of those spins carries a magnetic moment of approximately 9.27 times 10 to the minus 24 joules per Tesla, a quantity called the Bohr magneton, and that single number is the brick out of which every magnet on the planet is built. You can locate the structures involved on the magnet in your hand. The bulk of a common ferrite magnet is iron oxide. The electrons that matter are the 3d electrons of the iron atoms, the outer shell that is not filled, and in metallic iron, each atom contributes roughly 2.2 unpaired Bohr magnetons to the lattice. Hold that figure, 2.2 Bohr magnetons per atom. Multiplied across the roughly 10 to the 22 iron atoms in a gram of metal, that is the cooperative arithmetic doing the work in your fingers. Now the harder question. If every electron carries a magnetic moment, and your body contains something on the order of 10 to the 28 electrons, why does your hand not stick to the steel along with the magnet? The answer is the Pauli exclusion principle, formulated by Wolfgang Pauli in 1925, which forbids two electrons from occupying the same complete quantum state. In almost every atom, the lowest energy way to satisfy this rule is to pair electrons with opposite spins inside the same orbital. One up, one down. Their magnetic moments are antiparallel and they sum to nothing. Carbon does this, oxygen does this mostly, copper does this. Your skin, your bones, the plastic casing of your fridge, the aluminium of a soda can, all of these are crowded with electrons whose magnetic moments are bookkept against each other and net out to nearly zero. The fact that most matter is non-magnetic is not the absence of a phenomenon, it is the visible signature of pairing. In iron, cobalt, nickel, gadolinium, and a handful of compounds, the orbital geometry leaves some electrons unpaired by default. That unlocks the first condition for magnetism, but it is not the second condition, and the second condition is the heart of the whole story. The second condition is called the exchange interaction. It was identified by Werner Heisenberg in 1928 and by Paul Dirac independently the same year, and it is not a magnetic force in any classical sense. It is the electrostatic energy difference between two electron wave functions arranged with parallel spins versus anti-parallel spins, mediated by the requirement that the total wave function must be antisymmetric under exchange of the two electrons. Define that term inside this sentence. Antisymmetric means that swapping the labels of two electrons flips the sign of the wave function, which is the mathematical face of the Pauli principle. When the spin part is symmetric, which is what parallel spins produce, the spatial part must be antisymmetric, which means the two electrons are statistically held farther apart, which means their electrostatic repulsion is lower, which means the parallel configuration can actually be the lower energy state. In iron, the energy gap that favors parallel alignment between neighboring 3D electrons is on the order of 0.1 electron volts per pair. That is a Coulomb energy wearing a Pauli mask. The force you feel through the air at your fridge is, in mechanism, an electrical energy difference being made visible by a quantum bookkeeping rule. It is not magnetism in the everyday sense. It is electrostatics filtered through antisymmetry. There is a pharmaceutical equivalence worth pausing on, because magnetism is one of the rare places where a free quantum effect is sold back to industry at enormous markup. The active element inside a clinical magnetic resonance imaging machine is a superconducting coil cooled with liquid helium to generate a field of 1.5 to 3 Teslas. A research-grade rare earth permanent magnet on a laboratory bench can already produce a surface field of about 1.4 Teslas without any electricity at all, generated by exactly the same exchange interaction operating in a neodymium iron-boron lattice. The body of the magnet is doing for free what a $4 million hospital machine does with cryogenics and current. The same physics. The same Bohr magnetons summed across a lattice. The same Heisenberg exchange holding the spins parallel. One is given to you by geology and metallurgy. The other is sold as a billable imaging session. The molecular machinery is identical. The price is not. Now stack the mechanisms that are running simultaneously in the magnet under your fingers. The first is alignment of unpaired 3D spins inside each iron atom, according to Hund's first rule, which states that within a partially filled shell, electrons maximize their total spin before pairing, a rule named for Friedrich Hund in 1927. That is what gives you the 2.2 Bohr magnetons per atom in the first place. The second is the short-range exchange interaction that couples neighboring atomic moments into parallel alignment across distances of a few angstroms. The third is the formation of magnetic domains, regions typically between 100 nanometers and 100 micrometers across, inside which the exchange interaction has fully aligned trillions of atomic moments, but between which the orientations differ to minimize the total magnetostatic energy of the bulk piece. A piece of unmagnetized iron is not unmagnetized at the atomic level. It is fully magnetized inside every domain and only zero on average because the domains point in many directions. The fourth mechanism is domain wall motion. When you bring an external field near the metal, the boundaries between domains, which are themselves complicated structures called block walls, about 100 atoms thick, in which the spin rotates gradually from one orientation to the next, physically migrate. Domains aligned with the external field grow at the expense of those that are not. The fifth mechanism, operating against all the others, is thermal randomization. At any temperature above absolute zero, the atoms in the lattice are vibrating, and those vibrations couple to the spin system through spin-orbit coupling and try to scramble the alignment. The competition between exchange energy and thermal energy has a sharp resolution point named the Curie temperature, identified experimentally by Pierre Curie in his 1895 doctoral thesis on the magnetic properties of bodies at various temperatures. For iron, the Curie temperature is 1043 Kelvin, which is 770 degrees Celsius. Heat a fridge magnet past that, and it forgets it was ever magnetic. Cool it back down in zero external field, and it remains forgetful, because the domains reform in random orientations. The 770 figure is the number to remember, because it is the temperature at which the exchange interaction loses its quiet war against vibration. The exchange holds. Then, thermal noise wins. Then the order vanishes. There is an honest evidence accounting to lay out, because this niche is corrupted by overstatement, and you deserve calibration. The Bohr-van Leeuwen theorem is mathematically rigorous and uncontroversial. The existence and quantization of electron spin is established to better than 1 part in 10 billion by measurements of the electron magnetic moment, currently the most precisely tested prediction in all of physics. The Pauli exclusion principle and the exchange interaction as explanations of ferromagnetism are textbook consensus, calculable from first principles, and confirmed by neutron scattering experiments that directly image spin alignment in crystals. These are strongly evidenced. The picture of clean rectangular domains, separated by smooth block walls, is physically real but simplified. Real domain structures in commercial magnets are messier, with pinning sites at grain boundaries, lattice defects, and impurity clusters that are still active areas of research. That belongs on a middle shelf, physically grounded but not fully predicted from first principles. Speculative territory is occupied by some exotic phases, such as quantum spin liquids in materials like Herbert-Smithite, where the ground state involves spin entanglement that does not order even at the lowest temperatures reachable in a dilution refrigerator. Those are real materials with real published measurements, but the theoretical descriptions remain contested, and any video that tells you the matter is settled is overselling. The fridge magnet itself is settled physics. The frontier is elsewhere. Worth knowing which shelf each claim lives on. There is one more reframing of the central number, because the Bohr-van Leeuwen result is the line that turns this entire topic from a curiosity into a piece of evidence about the structure of reality. Classical physics predicts zero magnetization for every material. Your fridge is decorated with counterexamples. Each one is a falsification, performed at room temperature, requiring no instrument more elaborate than your hand. The magnet you touched at the start of this is not a demonstration of magnetism in the way a thermometer demonstrates temperature. It is a demonstration that the deepest layer of physics is not classical. Bring the magnet back to the steel. Feel the snap one more time. That short pull through a millimeter of air is electrons obeying Pauli, atoms aligned by Heisenberg exchange, domains restructured by an applied field, all of it summing to a force in your fingertips through a mechanism that Newton could not have written. The fridge holds the proof. Touch it again. The universe is quantum.